Okay, we're going to do a couple observations here. I have a bunch of different f of x functions here. They're all x squared plus a number. So let's observe something here. If we take the derivative of x squared, we get 2x because the constant gets wiped out. If we take the derivative of x squared plus 1, we get 2x because the constant 1 gets wiped out. If we take the derivative of x squared plus e, we get 2x because remember e by itself is e to the first, which is a constant. If we take the derivative of x squared plus pi, we get 2x because the pi gets wiped out. And we take the derivative of x squared plus 1/2, we also get 2x as the 1/2 gets wiped out. So I think we can make a conclusion here. If the derivative of some function is 2x, then that function is not really a function. It's really several functions. Okay, we would say it's x squared. These were all x squared plus something, and that something was always a constant number. Okay, so x squared plus a constant. So if we have a derivative, there is not just one function that has that derivative. There are a family of functions that have that derivative. And the third consequence of the mean value theorem says that if two functions have the same derivative, then the family that they are part of is a family of functions that differ by a constant. So that leads us to a definition and a symbol that we're going to use to mean the undoing of differentiation. Okay, so here's how we write this. If I have a function capital F and its derivative is lowercase f, okay, so they took the derivative of capital F and it got me to little f, then we call big F an, not the, an antiderivative of little f. So antiderivative is not a person who's against derivatives, right? I'm not antiderivatives. It's an antiderivative, which means I am undoing the process of differentiation to get from lowercase f to uppercase f. So, but I could say of 2x is x squared plus 11. And there's a whole bunch of other ones. That could be x squared plus any number. And we still have a derivative 2x. Okay, but this is an example of an antiderivative, undoing the process of differentiation. In general, we'd say x squared plus c is the family of antiderivatives for 2x. Okay, so we're going to start to see opportunities, situations where we're going to have to undo the derivative rules that we know, or at least some of them, some of the simpler ones. Okay, for example, we may be told, hey, f prime of x is a function. And what is the function it came from? So we have to reverse the rules in our head. So the first rule we're going to reverse is the power rule. So if I have a power of x to a number, and it's a derivative, where did it come from? Okay, so let's talk about taking the derivative of a power function. What do we do? And then we're just going to reverse that process to undo it. Okay, so if I have the derivative of x to the n, let's write down the steps. What do we do first? Okay, we multiply by the exponent, right? Multiply by exp. We brought the n down in front, right? And then we did what? We subtracted 1 from the exponent. That's how you took the derivative. So if we're going to do the antiderivative, we're going to go backwards. Okay, so to undo that, what are we going to do first? Well, we're going to add 1 to the exponent, because I need to undo the subtract 1. And then instead of multiply by the exponent, the new exponent, I'm going to divide by the new exponent. So that's my process for undoing the power rule. So if I have x to the n is the derivative of f, then the antiderivative of f is going to have to be what? Add 1 to the exponent, so that gives you n plus 1, and then divide by that new exponent, n plus 1. And then I have to put a plus c, because any constant would still have the same derivative, x to the n. All right, let's do some examples. If f prime of x is x cubed, then to go to f, I have to add 1 to the exponent, so that becomes to the 4th, and divide by that new exponent. And then we have to add a constant. To do f prime equals 6x and go backwards, we're going to add 1 to the exponent. That gives me x squared. So that 6 is still there, and I need to divide by the new exponent of 2, which would be 3x squared, if you like. Okay, what if it's just a 10? Well, that's technically 10x to the 0, right? So to go backwards, what do? We add 1 to the exponent. So we get 10x to the first, divide by the new exponent, which is 1. What if it's a square root? Well, this is really what? X to the half power, right? We've seen that 1,000 times. So to go, oops, I forgot the plus c here, and I forgot the plus c there. Hopefully you caught me. Don't forget the plus c. My calculus teacher used to have an expression when you do these type of problems. Okay, no c's, you get d's. So be careful. Don't do what I just did a couple times. All right. So to go from f prime to f, what are we going to do? We're going to add 1 to the exponent, which means I'm now at x to the 3 halves, and I'm going to divide by the new exponent, 3 halves. I'm going to remember my plus c this time, and I'm not going to leave it like that because that's just bad style. Flip the denominator and make it a multiplication problem, so I have 2/3 x to the 3 halves plus c. And the great thing is, if you're not sure if you're right, you can always take the derivative of your answer and see if it matches what you started with. Okay, can you find the plus c is a big question. The answer is yes, but you have to be given what's called an initial condition. In other words, this is a dot or a point on the curve that's known. If this is given to you, then there is only one answer, only one curve will have this derivative and go through this point. So let's take a look. I'm going to go backwards using the power rule. So 3x to the second divided by 2 plus, this is really 4x to the 0, right? So 4x to the first over 1, I don't really have to write the over 1, plus c. Okay, so if I clean that up a little bit, I'll get 3 halves x squared plus 4x plus c. Now, because I was given a point that the curve actually passes through, 1, 5, I can find the c. So 5 is equal to f of 1 is equal to, when x is 1, you get 3 halves times 1 plus 4 times 1 plus c. Let's convert everything to halves real quick. So 10 halves equals 3 halves plus 8 halves plus c. So it looks like c is going to be equal to -1/2. So in certain cases, you can find the mysterious c if you're given an initial condition. Okay, let's do a quick application of this, which is kind of fun. I have two statements here. It says, in the United States, the acceleration due to gravity is approximately -32 feet per second. It's a constant. It doesn't change. So if we're talking about a falling body, vertical falling body, then the acceleration due to gravity is always -32 if there's no air resistance and other factors like that. In the metric system, which is almost everywhere else but the United States, we do things in meters, so there the acceleration due to gravity is roughly -9.8 meters per second. Okay, so let's work backwards from acceleration. Since acceleration is a second derivative, let's work backwards to the original function to find the formula for a falling body's position, which is a big thing in physics. And it's kind of fun to do here. So if we go backwards one step, that's the velocity function. I need the antiderivative of -32. That's going to be -32 t is the variable here, because remember this is really t to the 0. This is also t to the 0. Okay, and don't forget your constant over here, and so we're going to do the same thing over here. -9.8 t to the first plus a constant. Now, this constant has kind of a special role. Notice that if you plug in 0 for t, I'll do that in red here. Okay, v of 0 would be equal to 0 plus c. So your c is really v of 0. Okay, v of 0. And v of 0 in the physics world would be called the initial velocity. Physics students probably write it as v sub I. Sometimes it's also written as v with a 0. This would be like v initial. This is v naught, v at time 0. So we could rewrite the above equation as the velocity at time t is equal to -32 t plus this number v naught or v initial, whichever one you like to use. Same thing over here for the metric system version. Negative 9.8t plus v naught, or v initial. Okay, now let's get to the position function. We've been using S to stand for the generic position function, even though this is vertical motion. All right, the antiderivative, what am I going to do? Negative 32 t to the second over 2. That gives me negative 16 t to the second plus v naught, or v initial, times t plus another constant. Over here, we're going to get negative 9.8 t squared over 2, which is negative 4.9 t squared, plus v naught, or v initial, t, plus a constant. And again, this constant has a special role. We'll notice that s of 0 would cancel out the other two terms and is equal to your constant. Okay, and that's going to be called either s naught or s initial. So if you're in the United States, this is the equation for the position of a falling body, negative 16t squared plus the initial velocity times t plus the initial position. And if you're in the metric system, this is the equation physics students might recognize. Maybe some different variables are used from time to time, but negative 4.9 t squared plus v naught t plus s naught. So you can memorize those or not, but I think you could always work backwards if you had to get there. So let's just do that real quick. To change things up, Shelby Quarter is at the top of the cheerleader pyramid. Her feet are 10 feet above the ground. So what does that mean? It means her initial position, we're going to measure the position of her feet here, okay? Her initial position is 10 feet. So that tells me a couple things. It tells me we're in the United States, so we're going to use the feet equation, not the meters equation. She is thrown upward with a velocity of 12 feet per second. So I have a v initial. She's thrown upward, that's positive velocity, so that's 12 feet per second. It says find her position function. Let's say I totally forgot what the equation was, but I should not forget that the acceleration due to gravity in the United States is negative 32 feet per second. I can then work backwards, do an antiderivative. Here's my constant. Now what's my constant equal to? Well, if I plug in 0, I'm going to get v of 0 equals 0 plus c. So c is the v of 0, and the v of 0 was 12. Okay, so I can erase that c, replace it with the 12. And then to get to the position function, I need another antiderivative. Negative 16t squared, that's after adding 1 to the exponent divided by 2, plus 12t plus another constant. And what's that constant? Well, if time is 0, those first two terms cancel, and you get c is equal to s naught, and s naught is 10 by the given in the problem here. So for this problem, this would be the position function for Shelby, or Shelby's feet, I guess, above the ground. And then we can ask all the same normal questions we ask about falling objects, or just objects in general. What's the velocity? When do they change direction? When are they at rest, etc.